Last time we talked about the Bohr model, and I wanted to clarify a few points with the Bohr model and explain things so it makes a little bit more sense before we move on to a new concept of orbital diagrams. So Bohr models, we established last time that we can have 2 electrons in the first shell and 8 in every other shell. And that 8 in every other shell is going to change relatively soon. But for right now, we're just saying that every other shell holds 8. By the way, I wanted to point out so that nobody's confused that these terms shell and energy level mean the same thing, and I'm going to be using them interchangeably. So make sure you recognize that shell and energy level mean the same thing. Next, I wanted to say that the outermost shell is really the most important shell for atoms, and we call that the valence shell. It's the most, it can hold up to 8, and its goal is to hold up to 8. So, and again, when we go over periodic table trends, we are going to explain why that is a little bit more. But let's talk about why the first shell can hold 2. And when I'm talking about the first shell, I'm talking about the one closest to the nucleus, so that's one right there. And then this would be the second shell, this would be the third shell, and this would be the valence shell. But let's talk about why the first shell only holds 2 electrons. So let's look at our periodic table up here and see let's look at the first row of the periodic table. So row 1, this one right here. And let's count how many atoms we have in that row. So we have one run right there, and the second one right there. So we have 2 total atoms in the first row of the periodic table. And if we think of, for today's lesson, let's think of all atoms as being uncharged. And so in the first row of the periodic table, if an atom is uncharged, then it can fit up to 2 electrons. So first row of the periodic table can hold 2 electrons. And then let's count how many atoms across the second row is. So we have 1, 2, 3, 4, 5, 6, 7, 8. Interesting. We have 8 electrons that can fit in the second row of the periodic table. And like we said, we can fit up to 8 electrons in the second energy level. Interesting. Let's look at the third row of the periodic table now. Again, we're going to count, and we're going to get to 8 electrons in the third energy level, or the third row of the periodic table, which is going to correspond to 8 electrons being the most that can fit in the third energy level, and so on. And we'll talk about how, once we get further along, this one will no longer be 8, and then these will be a different number. But we're going to talk about that in a different class in the future. But for right now, we're going to think of the first energy level can hold 2 electrons, and every other energy level can hold 8. Another important thing with the Bohr model is that I've been drawing them like this one over here on the left, where I've had the energy levels equally spaced out, and and by doing that, it's easy to see the different energy levels and the electrons, and you don't mix up anything as you're writing down the number of electrons. But so like if I had 2 electrons in this first one, when I write the 2 electrons, it's not it's not getting in the way, especially when we get to the outer orbitals, when over here they're like so close together. So but I do want to point out that technically it's more accurate to draw it like the one on the right here, because something that is true about energy levels is that they converge at high energy levels. So high energy levels converge at high energy, meaning they get closer together the further you get from the nucleus. So the further you get from the nucleus is the higher the energy level, and the further you get from the nucleus, the closer each energy level comes to one another, or gets to one another. So technically, an atom is going to look more like this one on the right. However, it is totally fine for when we're drawing Bohr models to draw it as we are drawing it this way on the left. However, this point of that they converge at high energy levels, I'll just tell you that that's an important thing that you're going to have to know, and that's going to be a question on our exam. So you don't have to draw it that way every time, but know that that is true. So when you are taking the exam and I ask you a question, you get that one right. So now I want to talk about what an orbital diagram is and how it compares to a Bohr model. So an orbital diagram is really just another way to draw an atom, but specifically it is representing the electrons in an atom. So we talked about how for this lesson, we're just going to consider all atoms as uncharged. And I'm going to do my first example is going to be oxygen, which we'll do in a little bit. But if I look at oxygen, we know that oxygen has 8 protons. And an uncharged oxygen is also going to have 8 electrons. So the only uncharged element in existence that has 8 electrons is oxygen. So let's keep that in mind going forward. With orbital diagrams, it's going to be important to first categorize the periodic table as into different segments. And that's how we're going to be explaining the different orbitals in these orbital diagrams. So let's go through this first part of this periodic table, this part on the left. We're going to call this the S block. And also, if you notice, there's a little spot that seems to be missing right here. That's because helium has a lot of properties to where sometimes it's more similar or more accurate to have it written over there. Some periodic tables will even have the helium written over there. But keep in mind that this helium is also part of the S block. Next, we have the P block. So the P block, and I'm going to do it in a different color so you don't get it mixed up with red. But this P block over here are going to be, it's going to be the ones over here. I'll explain the numbers associated with each one in a minute. Next, we will have the D block, and that's in the center here. That's the D block. And then lastly, we'll have the F block, but that one is going to really be the least important one for this class at least, because it's a lot more confusing. So we're not going to get into the F block too much in this class, but it does exist and it's located down there. And the numbers associated with each one is just going to be how wide it is. And so the S block can hold, let's see how wide it is. So there's one atom here and another one here. So it is 2 atoms wide, and we're going to say that it's 2 electrons wide. It can hold 2 electrons. So we're going to say 2, and I'm going to do, I typically do electrons in green, so I'm going to continue that trend. So it can hold 2 electrons. The P block is going to be the next one, and I'll explain that in a second, but the P block, we're going to count how wide it is. 1, 2, 3, 4, 5, 6. And so it can hold up to 6 electrons. And then the D block can hold 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. The F block is a little bit more confusing because for whatever reason it appears to be 15 wide, but there's 14 electrons that it can hold. So we're just going to remember that it can hold 14 electrons, but the reasonings why it's 15 wide, we won't get into that. You can email me if you have questions with that. But so the orbital diagram is a way to specifically represent an atom's electrons. And we have these different orbitals that the electrons are going to reside in that can hold a certain number of electrons in each. So I am now going to draw out oxygen in a Bohr model of oxygen, and let's do oxygen 15. So 15 is the mass number, and we will calculate the number of protons. The number of protons is just that number right there. So it's 8. So 8 protons. Next, there are 7 neutrons. And then lastly, since it's uncharged, the proton number and electron number are going to equal one another. So there are 8 electrons. All right, drawing this in a Bohr model now. We have 8 protons in the center, along with the 7 neutrons. We're going to encapsulate that in the nucleus. Even though there's not technically a capsule here, we'll just draw it to represent that that's all part of the nucleus. And then let's draw our first shell. And then we will draw our second shell. And the first shell can hold up to 2 electrons. And if I didn't make it obvious before, we can look at the periodic table. The first row can hold 1 electron here and 1 electron here. So that's why the first shell holds 2 electrons, because there's only room for 2 electrons to be held. The second shell can hold up to 8 electrons, because when we count across this one, we get 1, 2, 3, 4, 5, 6, 7, 8. So the second row can hold 8 electrons. That's why the second shell can hold 8 electrons. So, however, there are 8 total electrons for oxygen 15, and there are already 2 written in the first shell, so we only need 6 more electrons in the second shell. All right, I'm going to move this over so that we have a little more room. All right, that should be fine. All right, next, let's draw our orbital diagram and pay attention to these rules written here so that we draw it correctly. So oxygen 15, we're going to start every orbital diagram with an arrow pointed up that is labeled energy. So this is to indicate that the higher the energy level, which is the further from the nucleus, it's just an axis to represent energy. But remember, we said that the closer to the nucleus, the lower the energy level. The further from the nucleus, the higher the energy level. So that's to indicate that. So we could even signify that the nucleus is down here. But you don't have to write the nucleus is down there, but just write the energy write energy to label your axis. All right, we're going to start filling in our orbitals. So orbitals are going to be represented by boxes, and then the electrons are going to be represented by electrons. So I said that an orbital diagram is a way to represent an atom's electrons. And we'll say that electrons are represented by arrows. All right, and then also the arrows are going to be pointed up and down, and just to clarify, I'm going to be drawing my arrows as like little half arrows like this and this, up and down, but it is totally correct to also draw them like this, and they like full arrows, and they mean the same thing. So let's start drawing our orbital diagram, and so our first orbital is going to be on the first energy level. So looking at our periodic table, we have our energy levels as the row number. So first energy level, second energy level, third, fourth, fifth, sixth, seventh. And those are going to correspond to the energy levels in the Bohr model, and then also the energy levels in this orbital diagram. So we have our first energy level is going to be a box right here, and we're going to label that as 1. We have a 1 right here, and both of the electrons here are going to be part of the S block. Okay, so we're going to label this 1s. And I'm going to fill in my electrons. So 1 arrow pointed up, 1 arrow pointed down. But oxygen has more than just 2 electrons. So we're going to have to move on to the next orbital. The next orbital, and I like to, one thing you can do with your periodic table, you can kind of cross off where you're at, and you keep going until you get to the element that you want to. So we just established that we crossed off this one and this one, and we are now at where lithium's at. So again, we are now in the second energy level, and specifically the S orbital. So I'm going to draw in another box, and this one is located in higher energy level. So it is not the first energy level, it is higher energy level. Just like in our Bohr model, it is located further from the nucleus. And we're going to label this 2s because it is the second energy level and the S orbital. So I'm going to draw an arrow up and an arrow down, and now I have 4 electrons drawn. However, again, we have 8 total electrons, not 4. So we need to keep drawing more until we get to oxygen. We can cross off where we're at on the periodic table. We have the 2s orbital filled in. And then now we are moving on to the p orbital, the p orbital. And so we're going to draw another box here on the periodic table. And technically the p orbital is a little bit higher energy than the s orbital, even though they're at the same energy level. Kind of confusing, I know, but let's just make it easy and just remember to write the p orbital slightly higher than the s orbital, but not incredibly higher. So just slightly higher. So we have 2p, and then we're going to fill in the electrons that are going to go into this one. So let's count how many more electrons we need. We have 4 already, and we need to draw in, we already have 4, and there's 8 total, so we need 4 more. So I'm going to draw in 1 electron per box at a time before I go back and fill in any boxes with 2 electrons. And here is why. We're going to look at our rules. So no more than 2 electrons can occupy a suborbital, which is one of these boxes. So we can't have more than 2, so we haven't drawn more than 2, so we're good with that. And the electrons must have opposite spins. So if you have 1 electron pointed up, then the other electron inside of the box needs to be pointed down. So we did that. Electrons are placed in orbitals of lowest energy level first. So we filled up the 1s before we filled up the 2s, before we filled up the 2p, because 1s is the lowest energy level. Notice it's located lowest on the energy axis, and the 2p is highest on the energy axis, so it got filled in last. And then Hund's rule, and by the way, I don't care that you know the names of these rules, just make sure you're following the rules. Hund's rule is that every orbital in a sublevel is singly occupied before any orbital is doubly occupied. So all electrons in singly occupied orbitals have the same spin. That's an additional thing. So every one of these boxes here has to have 1 electron or 1 arrow before any of them can have 2. So we should never have 2 electrons in this box unless these other boxes are also filled up. All right, so we're going to double check our answer here now, and we see that, first of all, we counted. We have 1, 2, 3, 4, 5, 6, 7, 8 electrons drawn in this orbital. There are also 8 electrons that we calculated and 8 electrons drawn on our Bohr model. So therefore, the number of electrons is correct, so we must have done something right. Next, let's take out our highlighter and compare this side by side to the Bohr model. In our first energy level, this first energy level here has 2 electrons. And that's going to correspond to this first energy level up here in the periodic table. And it's also going to correspond to this first energy level on our orbital diagram. Next, the second energy level on our Bohr model has 6 electrons. All right, second energy level, second one from the nucleus. And then if we look here, we have a 2 here and a 2 here. That's to indicate these are both on the second energy level. And then we can also correspond this to the second row of the periodic table, second energy level. And we see that the second energy level, if we count our electrons within here, we have 6 total electrons in here because there are 6 electrons on the second energy level. So we see that the electrons, we have the correct number of electrons and the electrons are drawn in the right location. And then we also abided by all these rules so that we don't, so it looks like we did this one correctly. And let's do silicon 30. So let's first calculate how many protons, neutrons, and electrons silicon 30 has. So we can look at the number of protons by just looking at the number on the periodic table next to silicon. So there are 14 protons. And then the number of neutrons is going to be 30 minus 14, so 16 neutrons. And then lastly, it is uncharged. So the number of electrons is going to be the same as the number of protons. So 14 electrons. We can now draw our protons and neutrons in the center, in the nucleus. And then our electrons around it. First energy level. Second energy level. We might even need a third energy level. All right, so the first energy level, if we recall, can hold up to 2 electrons. The second energy level can hold up to 8. And right now we have 2 plus 8, we have 10 total electrons drawn, but there are 14 for silicon. So we need to draw 4 more. The second energy level can only fit 8, so the last 4 of them are going to have to go on the last energy level. So we now have 14 protons, 16 neutrons, and 14 electrons drawn in. So we are going to move this over so we have a little more room, and then draw our orbital diagram side by side so we can compare the two. So in orbital diagram, we are going to have an arrow pointed up, and we are going to label the axis energy. If you really want to be lazy, you can write E, but if you don't write the label for the axis, you're going to miss some points. Some easy points. So let's write our first orbital now. So our first orbital is going to be the first row of the periodic table and the S block, or the S orbital. The first energy level and the S orbital. So it's going to be the 1s orbital. And if you want to pause and see if you want to do it yourself while I work through this, you're welcome to do that too. But 1s, we're going to fill in the electrons, 2 electrons. All right, so we've got our, let's fill them in on here as we go as well. So boom, boom. Next, there are more electrons than just 2. We need to move on to the second energy level and the second s orbital. So we're going to go boom. And this is the next thing on the periodic table. We did 1s already. Now we're going to have to go to 2s. So start where lithium's at. So we are on the second energy level in the s orbital. And draw in our electrons. So we have 1 electron up, 1 electron down. We can cross off on the periodic table where we're at. 1, 2. Next, we can move on to keep moving left to right, and we get to boron, and this is part of the p orbital. So the p orbital is going to, you can hold up to 6. So 1, 2, 3, 4, 5, 6. And so we need to draw 3 boxes because 2 electrons can fit per box. So we need 3 boxes so that it has all 6. Question, can you say, hey, if I only need to draw a couple of electrons in the p orbital, can I just draw some of the boxes? No. And that's why I'd encourage us to just draw the boxes connected so we never forget to draw all 3 boxes. So you have 2p here. We're in the second energy level, and we are in the p block, or the p orbital. So 2p, and we are going to need to fill this up all the way because silicon is not in this energy level. So we need to fill this one up all the way. So 1, 2, 3, 4, 5, 6. We have, and then we can cross off on our periodic table where we're at. 1, 2, 3, 4, 5, 6. And notice how we are still not at silicon. So we still have more to draw. So where are we next? We move left to right. We are all the way right. So we're going to have to go down on an energy level to the next energy level 3, the third energy level. And we're going to be here. This is the third energy level and the s orbital. So we will have, we will draw the third energy level here, 3s. Let's fill in our electrons. 1, 2. We can cross off where we're at. Boom, boom. And then next, we can fill in where we're at on, we'll keep going across. So we don't have all the electrons. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 electrons, but there are 14 electrons in silicon. So we need to keep going. What's after 3s? Well, let's keep going left to right. And then we're going to be in the third energy level in the p orbital. So we're going to draw our 3 boxes. Write down that it is the third energy level in the p orbital. And then let's see how many more electrons we had to add. We have 12 electrons drawn, but there are 14 electrons total for silicon. Therefore, we have to draw 2 more electrons. So 1, 2. And make sure they're in different boxes because remember, every box needs at least 1 electron. Every box needs 1 electron before any of the boxes within that orbital can have 2 electrons. So those 2 electrons go in separate boxes, and we can now start double checking our answer. We have 14 total electrons drawn, just like we calculated that there should be 14 electrons. Next, we can take out our highlighter and see that the first energy level is supposed to have 2 electrons. The first energy level here has 2 electrons. Next, we can see that the second energy level has 8 electrons. The second energy level here, everything that's labeled with a 2, if we count how many arrows there are 8 arrows, indicating that there are 8 electrons. Next, let's see our third energy level. On the Bohr model here, we have 4 electrons in the third energy level. And then on this orbital diagram, we also have 4 electrons in the third energy level. So it looks like we followed the rules, we have the correct number of electrons, and the electrons are located in the correct energy levels. We can also finish checking our way through the periodic table, and we see that we filled in the 3s orbital here, and then the next was the 3p, and we can fill in 2 electrons here, and we stopped right at silicon because this is silicon that we just drew. So an orbital diagram, again, is a way to represent an atom based on the number of electrons it has, and it works because every uncharged atom has a predictable number of electrons. To clarify, silicon, for example, has 14 protons, and when it's uncharged, it has to have 14 electrons for those charges to cancel out. Because every uncharged atom has the same number of electrons as it has protons, we can know that this is silicon by just knowing the number of electrons. By just seeing the number of arrows drawn, we know this is silicon. So just a way to represent an atom based on the number of electrons it has. And I like to draw them side by side with the Bohr model so that you can double check your work just like I showed us. But we're going to be working more on this going forward. So hopefully that helped. I think that's everything I wanted to cover. I will see you all next time.